Then?
Ready to go.
Okay. Okay?
Okay, so this is the last of the lectures on this electromagnetics and interaction, X-ray interaction with matter. Now getting into more refractive index, these reflectivities that I've told you about that are so small, how small. So that's what we're going to do now. It says that's what we're going to do now. There we go. Which reminds me, was brought up by Elaine in the while we were having a coffee break. So there's a lecture tomorrow. It's kind of like a free lecture. We haven't decided, or a discussion of what we're going to do. So it was left open on purpose. So we'll see at the end of this lecture, what do we want to use that lecture for? Do we like to have a discussion? Or is there some topic you'd like to hear more about? And notice that there isn't, at least so far, I didn't see a lot of plasma physics but I don't know exactly the content of all the coming lectures. So it would be good if you gave me some ideas about things that how we should use that hour tomorrow. Okay?
Discussion might be good. The discussion might be good.
A discussion.
Try to see what comes up.
That would be fine with me, actually. Yeah. I mainly want to. I just don't want to come about 15 minutes before and someone say, "Okay, why don't you give a lecture on such and such?" Right? I need a little preparation. But if it's a discussion, we're ready to go. Yeah. So everyone think about that, and if that works, that's great. But okay. So now a different part of the story, which is how to use that refractive index to understand what's happening at an interface. What about normal incidence reflection? Why is it delta squared plus beta squared? And what is glancing incidence? Where does this angle, this critical angle, come from? And other things like that. The Brewster angle is roughly pi over 4. What is the Brewster angle? How does that work? You know? So that's what we're going to talk about now today. And this is just in general a sketch, not accurate, but just a sketch of refractive index versus frequency or photon energy. And basically in the visible region, you know, this is indicating refractive indices of something like 1.5. So the refractive index of glass in the visible is roughly 1.5 or something like that. And in the infrared, it's higher. And as you go down, each time you get near one of these resonances, there is something that happens at the resonance, but also, in general, these contributions to the refractive index, plus or minus, always have this lambda squared in it. So in general, there's they're getting smaller as wavelengths get smaller. So the formulas that we've derived here are general. They work either way, and in fact, if you look at the formulas that we have and apply them in the visible, you'll see that it makes a lot of sense. And so the lambda squareds will be there, the atomic density, and what these are and where the resonances are. But if you use these formulas, you could figure out that roughly the refractive index is going to be 1.5 in the visible. And that eventually, when you get on, there's always a big drop when you go across the resonances. And it was in the mathematics, but we didn't stop to talk about it much yesterday. But in general, you're going down with wavelength, and there's always a big change at the resonances. So eventually, it goes across. And even in the ultraviolet, there are some cases where, in the EUV wavelengths that we've been talking about, the refractive index isn't always 1 minus something. There are a few cases where it's 1 plus some small amount, just around the resonances. Whoops. So we talked about the wave equation, the transverse component of it, so that the transverse fields were driven by a transverse current density. This is written in vacuum, but we haven't determined what this is, and when we write it, it may come out that if this is written in terms of the same electric field, then we'll combine them all on one side of the equation, and the refractive index appears. we spoke yesterday about how to calculate these the current densities. So minus the charge, minus E, times the density of the scatterers, times some velocity. And if the velocity was driven by this propagating wave, then we used Newton's equation of motion. We wrote F equals ma, where the F was the Lorentz force, and the V cross B term didn't matter so much. And we got an expression. And if we want, this would what if we were in a material with an atomic density, and we had to sum over all of the electrons and all of the possible resonances. And in this lecture, I will show you the quantum mechanical expression for this. We would get this kind of a relationship where this sum over all electrons and over all possible transitions has to add up to what the total number of electrons is. Now, I could have shown you another line here. I was just realizing. So here is what that expression would be. That what we did yesterday, we would have seen that the velocity depended on the partial of E with respect to t. It's written slightly different than yesterday, but there are some others. I could show you another few lines in here, just like we did yesterday, but do you guys have these handouts? Did you get them? You all have them? Yeah, so if you go to the end, go to the very, rather than me trying to find this thing, go to the very end, not the last two. I'm counting back from the back. 1, 2, 3, 4, 5, 6. There's one that starts with the title, The Time Derivative of the Current Density, and it shows this equation of motion. Where are we here? Yeah, this one. Let me just hold yours up. Yeah. Okay. So that equation. So if you just look at that, it shows you an extra line of just the mathematics. This is the F equals ma that we wrote, and it's so as we did before for the bound electrons, and you assume an electric field that has an e to the I omega t in it. So everyone sees that? Oh, not everybody sees it. Let me do it. I'll waste a little time, and you'll see the fastest talk you've ever seen here. There we go. Yeah. So here's the current density as before. This is the force equation, the Lorentz force. This is our acceleration term, our damping term, our potential energy term. We assume a wave as before. I'm just showing the time dependence here. And if we put this time dependence into this equation, the time derivative once gets you a minus I omega in front of this. And for this term, you'll get a minus I omega squared. And then solve for x, and this will be what you get. And then if you take a derivative once, you'll get v. And if you take another derivative with time, you'll get the acceleration. Okay? And so that was the missing slide. Okay, I should have put that in a different order, but it's just like we did yesterday. And now I have to go backwards and get back to the front. Is anyone getting motion sickness? Yeah, so that's where this comes from. Okay, here. And eventually we're going to want the time derivative of the current density, so we're going to want actually the acceleration. But if we write J equals minus E, N, here's the atomic density, and V, that's this thing, we get all of these things. So this is showing that the current density has this form to it. And you can see, by the way, that whatever the sign is, depending, and if you put H bars on these, there'll be energies, right? So you can look at it either way, fine. But depending on which side of the resonance you are, there's going to be a change in sign. And that's what was happening with the curves that we saw. And that's why the refractive index in the end will be, 1 plus 0.5 for the visible light and 1 minus something if you're on the other side of the resonances. This increment from 1 is going to go one way or the other. Okay. So if you put this, if you then get this relationship for the current density J, and there's a subscript 0 here. And so for those who were here yesterday, remember that for an atom with all of these electrons distributed in different ways, there was an important phase effect there, okay, that appeared in the current density. And it went away in 2 cases. One was if the wavelength was so large that all of the electrons in the atom all saw the same phase and went together, then this phase effect went away. So that was why we were using soft X-rays and EUV rather than hard X-rays, where that assumption wouldn't work. Or the other case was in the forward direction. So when you're talking about refractive index, you are talking about forward direction. You're talking about a wave coming in, and it's not so much all the scattering, but how is the light bent or reflected at an interface. And so you're talking about forward direction, and so you can drop that phase effect. It doesn't contribute. And maybe a diagram would help to clarify that. But at any rate, that we would put in the subscript 0 here. This doesn't have that phase effect in it. It was dropped. And so here's an example. Did we find a pen last time? No. What can I say? If you remember this model of the atom that we had with all of these electrons in it, and we come in with some wave, and then we scattered off to some angle, and we had to take account of what was the different phases that the different electrons saw if the wavelength was short compared to the size of the atom. So we're talking about a hard X-ray or something, a wavelength of an angstrom or something like that. And so as it came through, there were all of these different electrons, and in that case, the phases that each of the electrons saw was different. And then if you were looking off at some angle, there was another phase. Ah, great. Thanks so much. So this is what we were speaking about yesterday. This was my atom, and there were different electrons, or electron clouds, but whatever. They were moving around, distributed, and there was an incoming wave with some wavelength lambda coming in, and we'd say, the way we did it was I chose it so that these two would see the same phase when this wave got there. These two would see the same phase to start with, but if the observer was over here, the path lengths were different here. So now there'd be a phase effect here, and it would matter what was the exact position of these things. And that's why the scattering would involve some phase effects and some interference effects, and the scattered radiation out at large angles would have some very large angular variations to it. Okay? That's why we had to worry about that phase effect that accounted for the positions of all of the different particles and what angle was this coming in and what was the scattering angle theta. All of that contributed to this. And again, we found that there were 2 cases where we didn't have to worry about the phase. One was that this wavelength was much larger so that every particle in here saw the same phase of the incident radiation, and the path lengths were not significant here in waves. And so the phase effect didn't matter if the wavelength was very long. But it also doesn't matter in the forward direction. So if you're coming in with a wave this way, okay, now you would say, well, let's look at these electrons. This one sees a different phase than this one, right? This one is starting to oscillate sooner than one that has a little bit. So there's a difference here, a phase difference here. I'm losing it, delta phi or something like that. But whatever there was an advance on this one, it's just the opposite in going to the detector. So in the forward direction, it doesn't matter either. This one starts oscillating earlier, but it takes longer to get here. So the difference in path length from the incident radiation is just compensated in the forward direction for what's seen. Okay? Because the actual path length for both of them is exactly the same. So it doesn't matter where these particles are or if they're moving around. It doesn't matter. In the forward direction, life gets easier. So in that case, I didn't have to put soft X-rays. For those of you who were here yesterday, the joke was, the reason for the title was I didn't want to have to deal with this problem. Okay. Oh yeah, and I should mention, the title of this book came from Professor Machette. I was struggling with how to have a title. I didn't quite have it, and now I did that. Okay, so that gets us up here as to why there's a subscript 0 and why when we write down the wave equation with this JT on the other side, it looks like this. And so there's the operator is acting on this transverse wave, but the transverse wave itself is driving the oscillations. So there's an ET on both sides. Let's combine them both onto one side and have a more complicated operator. And so now this is the operator operating on ET. So this is the propagation of a transverse wave in some medium now. Now we've gotten to the point where we're talking about an atomic density. So we're propagating in copper or something else. And so this combined operator here is multiplying on this. And this equation says something's got to be 0. But we don't want the electric field to be 0. We want to have a finite field propagating. So that means the operator's got to be 0. So this thing has to be set equal to 0 to know what is the dispersion relationship. What is the relationship between the frequencies that are going to come here and the wavelengths such that there's propagation with a finite field. And so we can take this equation and combine all of this stuff here into, well, we'll write this in the standard form of a wave equation. Okay? We'll take all of this and combine it and write it in the standard form of a wave equation that the mathematician would recognize and we would recognize. So this could be a water wave or an electromagnetic wave. And when we do that, in the standard form, there's this effect here which we call the refractive index. And we recognize that as being this thing. We say it's identically equal to. It's just representing all of these things. And this is what's letting us know if this, what's the phase velocity of this wave. So, yes, and it turns out that in the X-ray region, although the atomic density is very large, if you put some numbers, it's one of the homework problems on the online lectures, because this frequency is so high, this thing has a certain number density. For instance, this could be some, let's again say the copper atom or something. This could be like 10 to the 22 or so atoms per cubic centimeter. And you put all these parameters in and put in some X-ray frequencies, you'll find out that this is very small. So when you take the square root, you just get a half factor. Okay? And so that's quite accurate. So this is now our refractive index. It has this negative sign here, but again, that very much depends on whether you're above or below the resonance that you're talking about. So if the frequencies are higher than the resonance, they'll have a minus contribution. It's a phase effect. If the frequencies are below the resonance, then it goes the other way. So for the propagation of light through this window, the resonances are in the ultraviolet, and the frequencies are below that. The photon energies are below the resonances, and this becomes a positive. And in that case, the frequencies are visible light, not X-rays, and although this is a high number, this is also a high number, and this is where this, for green light in the glass window, all of this would give you a plus 1/2. Okay? And it would have this wavelength dependence on it that you would see in refractive index data. Okay, so now we have a refractive index and we have a wave equation, and this is just repeated at the top. Again, the sums have to be over all electrons in the atom and all of the possible transitions for each of those atoms. And quantum mechanically, you would have written it this way in terms, and you would introduce oscillator strengths, okay, for all of the electrons. And we just note that this has a real and imaginary part to it. So we can introduce those same the same atomic scattering factors that we saw when we did Thomson scattering and Rayleigh scattering. And so this thing, because we're just in the forward direction, we have this simple version, and it matches up perfectly to what we saw yesterday about atomic scattering factors. So, and again, these are multipliers of what is the scattering power of this object, this atom, compared to a single free electron. So at high enough photon energies, this will become, the frequencies won't matter anymore. High enough photon energies, this will be much greater than these two. These two will cancel out. This is a sum over G sub S. It's just this factor Z. So in the asymptote, this becomes the real Z. Okay? Again, recognizing how to combine all of these factors into a classical electron radius, we can then, just comparing these things, we can write the refractive index in this manner, where now it's, rather than all of these details of different resonances, they're combined into the atomic scattering factors, as shown here. Okay. So that is the refractive index. This is quite valid for all different regions of the spectrum, but it's a little bit too much to carry around in our head, so we write it briefly in this manner. Okay. Any comments or different views of this? Okay, so we have the starting material, and now we have a refractive index, and now we could go back to our electromagnetics book for the visible, and we could look at all kinds of things about reflection and that. So these would be things that you most likely did as an undergraduate or early graduate student, and that's what we're going to do next. So here's a quantum mechanical one, and I mentioned to you yesterday that I keep hitting the wrong button. You could look at the book by R.W. James on X-ray diffraction, I think it's called, or something like that. But it's a classic book. It's a wonderfully written book. And you would see these expressions, and you would see that he defines F, the real and imaginary part. He will, because he's working mostly with hard X-rays, he'll use that Z limit. He'll say that F0 prime or F01 is equal to Z minus something. A little bit different than what I wrote, but completely equivalent. Okay? And there are some other references here. Liebov is kind of an undergraduate atomic physics book, but it's got a lot of content to it, and it's extremely well written. And Corney's book on, I forget what it's, I said it yesterday, but I don't remember. It's a very good book about interaction of light with it's a quantum mechanics book for people who are interested in light and lasers. So it's a great book. I think it's Oxford Press, Oxford University Press or something. Oh yeah, so there was a question yesterday about how do you figure out this, how do you know F1 and F2? Where do you get these from? I mean, we look them up online, but where does that come from and how accurate is it? And so what happens is, for a real physical quantity, which involves some absorptive process or something, there is a relationship between the real and imaginary parts that is called the Kramers-Kronig relation. It's defined by the Kramers-Kronig relation. So if you want, you can read a little bit about it in the book, or there are other places much more, but there's a little bit of description there. But basically it says that they're related to each other by full integrals over the full spectrum of this mathematical form. So if you want to know F1, and if you already knew F2 over the full spectrum, you'd perform this integration. This is the Cauchy principled part, or you could do it in some other way. So F1 would depend on F2 over the full spectrum, and likewise F2 depends on F1 over the full spectrum. Okay, and so what actually happens in practice is that F2 is the absorptive part, if you remember. It's related to mu. Remember, there was a one-to-one relationship for that e to the minus rho mu x. So you put thin foils of all this material, or thin samples of gas, whatever, and for instance, in a synchrotron where they have a continuum of these X-rays, and you measure this for a full range of photon energy. So you've got F2 by measurements, and you have some theory to guide you So when you see little oddities or you're near the edges or something, you have a theory to sort of guide you, but you make measurements over the full spectrum. So you've got F2, and then you can figure out F1 from F2 by doing these full integrals. And so that's what's done. And if you go to this website where you can look up F1 and F2 for everything up to uranium over a very wide region of interest here, that's how they got these numbers. They went through the literature. They did measurements themselves, but Henke at first simply went through, Burton Henke simply went through the literature and got all of the information he could on as many elements as possible, eventually getting all the way up to uranium, and he published it. And then he and his group, and actually his wife, did the Kramers-Kronig integrals and figure out the real part also, and then they published it as delta and beta, and then his young colleague at the time, Eric Gullickson, took over, and for the last 10 years or so, Eric has been doing this, updating. Every year he updates it with more measurements and more calculations and improving the accuracy all the time. So this website has all of these things, but in answer to the question yesterday, this is where they come from. Okay. So we saw enough of these now, but there was a few people new in the room. What we started the lectures with was that if you looked at transmission of X-rays or EUV through thin foils, you would write the transmission as I over I0 intensities through a thin foil was an exponential e to the minus rho, the mass density, mu, a coefficient of absorption, times the thickness x, and this was the mu in centimeters squared per gram. Okay, and this you'd get from just measuring thin films. And there's a one-to-one relationship between mu and F2, the absorptive part. Looks different only because the scale is different. But so that's how you get these things. And from this, you get this. Okay? And this is some of the tabular work. And so those are all at this website that we talked about before. And we looked at this, again, for silicon and molybdenum. For various reasons, we were interested in that. But you also see where, for instance, in silicon, for those who were not here yesterday, these things are normalized to be in units of effective electrons. So the real part, if you get above the frequencies so that 1 over omega squared minus omega s squared doesn't matter anymore, then this will come to roughly Z. So for silicon, this will come to 14, and for molybdenum, it'll come roughly to 42. You have all this structure, and all of this is in there when you say 1 minus delta plus I beta. Okay. Now another thing you can do with the wave equation we had it in standard form is the operator was squared, and so you could factor it into two parts. And this is slightly different than what I wrote yesterday, but it's free. It's here. So you have these two factors, and again, if you want to know what are the natural modes that propagate in some medium, you again say, well, this is 0, but I don't want my field to be 0. I want to know what natural mode can propagate. So this is not 0. One of these two factors must be 0. And so here's one of the factors, and here's the other factor. And they're both propagating waves. It's just one that's propagating in one direction and one is propagating in the other direction. That's the sign. And they're propagating with a phase velocity of c over n. Okay? And so this, again, is just a standard electromagnetic theory. And the only thing that gets mentioned is this is a phase velocity. If you have these crests, what's the velocity that the crests are moving at? We call that the phase velocity. It's c over n. But there's another thing called the group velocity, which I haven't shown here. And it's the group velocity which carries information. And that's what can't go faster than the speed of light at whatever frequency in the medium. Not just period, just in the medium. And so even though we will have a refractive index a little bit less than unity, so that the phase velocity will be a little bit greater than the speed of light, it's the phase velocity. It doesn't carry information. It's the group velocity of many waves with some modulation that carries information. And so we're not violating any of Einstein's principle, and he's not worried that we're getting into bad territory here. Okay. Also, so if you take one of these factors and you say, okay, it's going to be 0, and you assume a wave of this form like we did yesterday, and you take these derivatives, the partial with respect to time of et, this is a constant, and this just brings down a minus I omega. So this term gives a minus I omega. The gradient is a vector, but at any rate, it would bring down a plus ik, okay, on this term, and you have a c over n. So this is what you get. So this being 0, this operator, gives you this relationship, and this is where you get the dispersion the simple dispersion relation for propagating in some medium n. And so you could say, you can just set this then, set this equal to 0, and you have a relationship between omega and k. And remember that this k is equal to 2 pi over lambda, so you're going to get your f times lambda equals c, or in this case, c over n. Okay? And you can also see, you can just solve here, the phase velocity is related to omega over k, which would be c over n. So that's the phase velocity. But, oops, did I miss something? Well, anyway, if you just set this equal to 0, you'll get your f lambda equals c over n. Okay? And then the other thing you can do rather conveniently, so we are assuming that we have these plane waves of this form, and we have a relationship between omega and k. And so here, that we just found on the previous slide, we can solve for k. How does k depend on the frequency and the refractive index? And let's just say that we have a wave that's coming into a medium. The frequency is set. Okay, it has some frequency, and in vacuum it has some wavelength. But when it comes to some interface with a material, the boundary conditions at the interface will always preserve the time dependence. If the electric field is going up on one side of the interface, it's going to be going up on the other side of the interface. At the interface, the time dependence is preserved. So it's the frequency that's dominated here. The k may vary, the wavelength may vary in the material, but at the interface, the frequencies are going to be the same. The frequencies are going to be the same everywhere. So the thing to do then, if you want to know what's going on in this relationship, is to assume that there is some frequency. You don't know what k is. You solve for it here and put this in here, and then just the one-dimensional version of this, where this becomes in the direction r. Substitute this in here, and this is what you'll have. Here's the minus I omega t, the first term, and this is the k, which is here, omega over c, and the refractive index, and then just multiply these things out, and you'll have all of these different factors which are easily recognized. So the first factor is just the propagation in vacuum, and this is just the retarded time. How far did you go? What's the phase? Then there's a phase shift term, which depends on delta. This is an oscillating term. There's no loss of amplitude here. But this one, with the beta, gives a decay. Okay. And so this is the decay term. This is how you can see right away how you could relate mu to beta. And beta depends on F2, so there's your relationship. And this is this oscillating phase. So phase effects, as in interferometers or propagating through some medium, there's a phase shift. This is how you would calculate that. And I wanted to point out something else, and I don't remember what it was. I guess we'll have to come back to it. Oh yeah, so if you made interferometers, you could measure this phase shift or something. I think I'm going to show that briefly. Yesterday we talked about getting the intensity. We got the pointing vector was E cross H, and then we said the magnitude of the pointing vector was the intensity, I called it. Intensity in watts per centimeter squared. And it depended on this epsilon 0 over mu 0 times the modulus of the electric field squared. But now we're actually in a medium. We were doing it in vacuum yesterday. But if we're in a medium, the refractive index comes in, and what comes in fact, is a real part of n. And so the average intensity, the bar meaning averaged over a cycle, so remember that broad and a half. If you put all of these things in that we had before, if you took this relationship, and put it in here for E, because you're taking the modulus, there's an E minus and there's an E plus, but the decay term stays and it gets squared. And so this is your relationship now between the intensity after propagating through some medium, a distance r, and it depends on beta. And we can just introduce an absorption length. When does it go to 1 over E? And that would be this absorption length, where beta we knew from before. And so we have now that the absorption length is this, some expression. And then we just recall and compare to what we did in the very first lecture, which people have been doing with X-rays since they were invented, was write it in this term. And now we can compare the mu and the F2. If you just see how those things compare, you have essentially a relationship between the macroscopic mu, this is what we were measuring through a foil of many atoms, with the scattering factor for a single atom. Okay, so you have a relationship between the macroscopic and the microscopic. And okay, so this was the relationship, and I said this was the phase term. So if you propagate through some medium, through some thickness, you'll get a phase shift of this amount here. And there are different ways that you could measure that, but all kinds of interferometers, uncountable probably, versions of interferometers exist where you take radiation and you split it into two parts in one way or another. There's all kinds of clever ways of doing this. And let's call one the reference wave and one the object wave. And so the light comes through, X-rays in this case, bounce off a mirror, come down, and bounce off what's called a beam splitter, and go to some detector. Or bounce off here, off the mirror, through the object, through some distance, delta r, and over here. So otherwise the path lengths are identical. So the phase propagation distance would be the same for both waves, but in going through this object, there'll be some phase shift, okay? And it depends on delta. So, for example, someone asked the question yesterday about the zone plate. If it's opaque, if it were gold, it would just block it out. But suppose it wasn't completely opaque. And I mentioned that nickel zone plates, somewhere around the nickel edge on the low side of below the absorption, the nickel zone plates often have a phase effect in there where there's a phase advance. So it's not all of the efficiency was controlled by the absorptive part, but there was actually, you could imagine having a zone plate, if you didn't have any absorption, where it was thick enough so that you got 180-degree phase shift as you went through the material. So you just, knowing delta at some photon energy, make the thickness enough so that you got 180-degree phase shift. So now you'd have a perfect zone plate. You know, there would be going through vacuum in the openings and then going through the material, it would come out 180 degrees out of phase. This would be the perfect zone plate, and I guess you'd be 100% efficiency. And sound fair, Alan? Ask the expert in the room.
100%.
Something. Yeah. Close.
I think about 70.
Okay. Okay. At any rate, you make a great.
You're always going to absorption, so.
Huh?
You're always going to get absorption.
Oh yeah, but I was. Yeah, we were taking the theoretical case.
But if you like if you have this sort of like a cuneiform lens,
Mm-hmm.
if there's no absorption, you could get 100% in theory.
Yeah, in theory. Okay, so we know that we have beta, and that's not going to be the case. But this is how you would calculate that phase shift that would be required. And if you have a nickel zone plate, you can include and you can calculate what is the contribution just by absorption, and what's the part from the phase advance. So that's all I wanted to mention here. In the X-ray region, it's a little bit difficult to make interferometers, or in the EUV, but they're definitely made. And there are some references, there's lots of references, but the difficulty is to make a beam splitter that's very flat, first of all. We want to have a wave coming on, a wave bouncing off, and going through our material. And so you need a flat beam splitter, but it has to be very thin for the EUV because of absorption. So there's just some practical issues of how do you make an interferometer. But if you want, we could talk about it more. There are such things. In the X-ray region, there are these Bond's-Hart interferometers using crystals. Because remember the crystal we said, if you got a high enough photon energy, in some of these silicon 111 reflections off crystals, you can get it pretty close to 100% of your X-rays through. And so, there you have absorption too, but the absorption is much less at higher photon energies. And also, in the crystal is this not Bond's-Hart. I got Bond's-Hart in my head. The Borman effect lowers the absorption considerably. And that is, in the crystal or in the multi-layer mirror, there's an incoming wave and there's a scattered or diffracted wave. And just at the Bragg condition, those things interfere in a way that puts the maximum of intensity in the planes between the atoms. So there's less absorption by the K shells. The L shells, the valence electrons are still there and scattering, and that's how it works. So in the X-ray region, there are the Bond's-Hart interferometers, and they work great, and people use that. Okay, so now we're going to go to reflection and refraction at interfaces, and just a few important things to get. And most of this is just a copy from whatever electromagnetics book you ever used. Okay, up to a certain point, except we're going to stick in a refractive index that for the X-ray region. And so we're going to have, this is the usual geometry. There's an incident wave. It'll have a wave vector. It has a frequency, omega. It has some K vector. If this is the vacuum side, or let's say, we'll know what this is, but it's a vector. And there's a polarization, and we usually break it up into two parts. We do a calculation where the electric field, my thumb, is in the plane of incidence or out of the plane, 90 degrees. So those are the two polarizations we consider. And we'll start with the typical angles measured from the normal to the surface, because that's what we always do in electromagnetics. We're going to find out in a moment that we're kind of interested in these narrow angles over here, so we will convert from measured from the normal to measured from the surface. But anyway, the incident wave now is our normal form that we've been using, and the refracted wave and the reflected wave, K prime and K double prime, look the same. They have the markings on the amplitudes and different wave vectors. And the question is, what are the angles and what are the amplitudes of the waves that go through? All waves have the same frequency. So the magnitudes of the Ks, in vacuum at least, are omega over c. Okay? And the refracted wave, it says, depends on refractive index, because in this case, this is vacuum, this is some material. And then you have boundary conditions that you need to apply at the interface, the continuity of electric and magnetic fields in certain ways. So I won't stop to spend time on this, because it's, again, exactly the same as any electromagnetics or microwave book that you looked at. And when you apply those things, one important thing is that if there's any periodicity along the interface, so the wave is coming in, it's a wave, it has some amplitude that's going, and there's a projection of that onto this plane. And whatever that periodicity is on the incoming wave, it's got to be the exact same on the other side of the boundary. So if there's an oscillation, again, you have a wave coming in here. Let's say this is one cycle. Depending on the angle, there'll be a component of that here, which is also one cycle. It's all at the same frequency, but spatially, whatever this spatial projection is onto this plane, the waves on the other side and the reflected waves all have to have that same periodicity. So that's what this expression is. The K, Kx prime, and Kx double prime all have to be the exact same. And when you say that, that gives you some relationship between the angles, and you immediately find out some really interesting things. So simply, you get that the angle of reflection has to be equal to the angle of incidence, and you also get Snell's law relating the angles of refraction with the refractive index. So all that came from just making this simple observation. So if it's not instantly obvious to you, just think about it, and sometime later today it will become really true, that the periodicities for all of these things along the interface have to be the same. And this is Snell's law. And we're going to use this in a moment to find out about the critical angle, where we're going to put in our information here for the refractive index. In fact, it's 1 minus delta plus I beta, and we're going to leave out the beta for a moment just to get the main result, and then we'll put the beta back in again. So we're not going to do this, but basically the boundary conditions on the tangential electric fields being continuous, and all of the other boundary conditions on the magnetic field, and Snell's law, we have 3 equations and 3 unknowns, and we solve them, and we get the amplitude of the refracted wave and the reflected wave, and then we form intensities as before, where these are going to depend on the amplitudes modulus squared. And so you can get the reflectivity, and now it depends not on the polarization, as I said before. So you have to do 2 cases. Any wave coming in of any polarization, you can split up into these 2 components. One in the plane, one electric field out of the plane, perpendicular to the plane. And you'll get this. This is the expression for the reflectivity of what's called S polarization. And we'll look at the P polarization later. It looks similar, it's slightly different though. But again, this is straight from your electromagnetics book, so this is not something special about X-rays yet, but we haven't put in the refractive index. So when we look at a couple of things, one interesting thing is to look at normal incidence. What happens when you go back here, this is the same expression, and you put in phi equals 0. Remember, phi was measured from the normal. So for normal incidence, if you put that in, this is going to be 0, this is going to be 1, so this is going to be 1 minus n, and the other one's going to be 1 plus n, modulus squared, and if you go through and put all of this in, this is what you get. You do all that algebra, this is what the result comes out to be. So for instance, so here's an example. You saw some examples yesterday. If you go to that website I told you about, or if you go to one of the appendices in the back of the book, for a couple of elements, there are some numbers there. But this is nickel at 300 eV. This is F1, and this is F2. Okay, and if you, from those, calculate delta and beta, you can see that delta is like 0.01, and beta is a little bit less than that. And if you put those in, you get a reflectivity of less than 10 to the minus 4. So this is what we meant by small reflection. And if you go further into the X-ray region, remember that the components of the refractive index went as lambda squared. So this is for 300 eV. If you go to 3 kilovolts, these things are going to be 100 times smaller. And if you go to 30 kilovolts, where many people will do experiments, these things are becoming truly vanishing. Okay? So this is one of the important results that we have to make note of. So that's why we introduced the red box. Okay? Another important one is, what about glancing incidence? Okay, so start with one polarization. And basically we're going to find that for very small angles, there's going to be great reflection, but for most angles, as we saw, it's going to be very small. So we're going to go through, and this is showing the full solution of it. And the earliest publication about this, you can see total reflection by X-rays, 1930s, give you some sense of when this. So if you go through this mathematics and you put in the refractive index as we know it, this is what you'll see as a result. This is now measuring from the interface, not from the normal, that was phi, but going around 90 degrees. This is measuring light coming in at glancing incidence angles. So for this particular example, and I forget what I calculated this for, but anyway, just some numbers here. This is showing that for small angles less than the critical angle, there's a total reflection in the case A, where beta is 0. There's no absorption. You get this very sharp thing. So I think Professor Michette showed you this yesterday. And then for varying degrees of beta over delta, you start to see an absorption effect even within the critical angle, and then it tails off. So this is a major use of an X-ray optic that's used in just about any experiment that somebody's doing. Okay? The KB optics was one example of that, but just plain mirrors are quite often used. But let's get a better handle on this. This is coming out of the mathematics. It's not quite intuitive, you know? What is this angle? What is this critical angle? So I think that's what the next slide is about. So this is just reminding you, this is a slide you saw before, just reminding you that just by using the periodicity argument along the interface, you got Snell's law. So now we're going to use Snell's law in the next slide. So here's our geometry now. Here's measuring angle phi from the normal, but adding up to 90 degrees is this other angle measured from the interface. And the angle of incidence and everything is shown here. This is this Snell's law. Now, leaving off the beta part for the moment, so we can just get a good understanding of this in simplicity, and says, consider the limit when phi prime goes to pi over 2, when this refracted angle is actually running along the interface. That's the best you can do with the refracted angle, right? The reflected angle is always going to be here, and it's always going to be equal to the incident angle, right? But the refraction, you can push it to the limit of just running along the interface, and that's about what you can do. I'll explain a little bit more about that in a moment. But in that limit, when this is, so you're making this angle closer and closer to the interface and watching this thing push down, and just where this is 90 degrees, you call this angle the critical angle for total external reflection. So that's what's happening here. When phi prime is equal to pi over 2, this is 1. This we call the critical angle, 1 minus delta, and then we want to just solve for this critical angle. So that's clear, right? This is 90 degrees, so this is 1. This we call the critical angle, that's here. Rearrange it to solve for this. These angles are complementary. We don't want to work with phi critical, because it's an art, we want to work with this angle, which is some easily remembered thing, like 1 or 2 or 3 degrees. Okay, so we switch here from phi to theta. This is the same as the cosine of this angle, so just using the relationship from trigonometry. So the cosine of the angle is this. This angle is very small, so we can expand the cosine as 1 minus the angle squared. Okay, there's a 1 on both sides, and you solve for the critical angle. It's twice delta square root. So this is the critical angle. So now if you knew delta, for like that slide we had before, for 300 EV and whatever it was, nickel, delta was like 0.01 or something like that, you can figure out what is this critical angle. So just at the critical angle, the refracted wave is propagating along the surface. And you might ask, well, what happens if I go a little bit less than the critical angle? What happens? And actually what happens, if you look at it in detail, is that at the critical angle, when you're just here, although the wave is propagating along the interface, there's an exponential decay into the medium, okay? And but as you move the angle in even closer, below the critical angle, the penetration depth becomes smaller, and so that's why there's a little bit of a rollover in the reflectivity curve. So that's called total external reflection. And this is to be compared to visible light of total internal reflection, which we didn't stop to talk about, but maybe we should have. So for visible light, there's a couple of common things that we remember. Let me see if I can get this right. For people who work in an optics lab or a laser lab, you'll have a turning prism. You'd like to turn your laser light 90 degrees, but you don't want to have a reflection. You don't want to incur losses, so you'll have a glass prism with an anti-reflection coating here and an anti-reflection coating here, like this. So at the wavelength you're coming in at, that's a problem. And if this is glass at 1.5, you'll find that there is a total internal reflection for visible light off this thing. So it's the same thing. There would be some penetration, some exponential penetration into the vacuum, but this would give a total reflection here, and all the light would come out. So this we call total internal reflection. For X-rays, because the refractive index is a little bit less than unity rather than a little bit more than unity, you get total external reflection. Another example, a couple of examples, if you're ever in a swimming pool, okay, if you're in a swimming pool and you go under the water and open your eyes, if you look straight up, you can see the sky and the blue sky and the clouds and everything. But if you look at an angle, you'll see everybody's legs sticking into the water, and you won't see out of the water, right? So there's another total internal reflection, and another one is a fish tank. If you come up and you look into the fish tank, you can see the fish. But if you look at the sides, you can't see the wall on the sides, right? Those are 3 examples of total internal reflection, and they all internal reflection because the refractive index is a little bit larger than unity. And here we have a refractive index which is less than unity, and we get total external reflection. And so we've learned now in this electromagnetic theory that if we come in at normal incidence, we get this incredibly small reflection. And in fact, at almost any angle, it's a very, very small reflection. But just at glancing incidence, at angles below the critical angle, we can get very high reflection. And how high? Now we get into a little bit of practical thing. Here we just took 1 minus delta. What if we put the beta back in? And this we need to do some, we don't need to, but we can do some numerics. Let me skip this one. So this was a theoretical curves with different assumptions of beta over delta, and no particular resonances or anything like that. But here's some from real materials of, you can see carbon, aluminum, aluminum oxide, gold. And these are showing as a function of photon energy, what does this reflection look like? So here's carbon for 2 different angles of incidence. What is the curve? What does the reflection curve look like? And you can see that as you go to higher photon energies, this is plotting in photon energies, but you also have to take into account the absorptive effects. So this is saying that if you had a carbon mirror, and you came in at these different angles in milliradians, what kind of reflection could you see? Okay, so in fact you can use these mirrors to cut out higher photon energies. The higher photon energies, meaning out here, there's no reflection; they get absorbed. Lower photon energies get through. So this is a low-pass filter. Okay, and this is showing aluminum and the aluminum absorption edges. But what about aluminum oxide? You made a nice, beautiful aluminum mirror, but you left it out in air, and it oxidized, and now you have some more absorption edges. And you can use these absorption edges, if you choose your angles right, to make your bandpass filter have some additional accuracy, specificity. And of course, gold goes out further. This is just a little thing, especially in plasma physics. Sometimes you want some moderate bandpass. You're not trying to be a spectroscopist and get a very narrow line, but you'd like some bandpass of perhaps a photon energy E over delta E of 4 or 5 or 3 or something like that, and you combine a mirror reflectivity versus photon energy, so you have some broad source of radiation, broad spectrum, and you'd like to see one part of it. So the mirror is a low pass. It's reflecting the lower photon energies, and you put one of those absorption filters, thin films that we were talking about before, that for very high photon energies it goes right through the filter, so high transmission, but there'll be some absorption edge here, and this is what it would look like. On the low edge of the resonance, there's a high absorption. Did I get that right? Yeah, low transmission at higher photon energies, looking at the blue curve, and for your transmission filter, and at lower energies, there's a higher transmission. So why am I saying that wrong? Yeah. Anyway, one is a low pass, and one is a high pass, and if you play with the material on the absorption edge, you can make what's called a notch filter. It's the name of these things, and they're also quite commonly used. They're not quite an optic, but a commonly used tool. And you might want to get some broad idea of the temperature of your plasma or something like that, not wanting to have a big, in this particular case you don't need it, a high resolution spectrograph, you might make several different, maybe 3 different notch filters in different regions and get some different chunks of the spectrum, and you'll have some idea of the temperature. The other was S polarization, now P polarization, where the electric field is in the plane, and the expression that you would get for the refracted and reflected fields are slightly different. The reflectivity expression not quite the same as what we had before, but if you look at it in normal incidence, you'll find that you get the exact same answer. It doesn't depend on polarization at normal incidence. They're both the same. So you get the same delta squared plus beta squared over 4. But there's a very interesting effect at a certain angle called the Brewster angle. And I think that's the next slide. Yeah. So P polarization, the electric field is coming in now, and the wave is coming in, and the electric field is polarized in the plane, and it's coming like this, and there's a reflection here, and a refracted wave. And so this is the business about, do we always have to look at scattering on the microscopic level when we're really looking at some macroscopic effect? But here's a case where you can understand the Brewster angle. At the Brewster angle, the answer is there is no reflected wave. The electric field in this geometry is 0. There is no. So this is Brewster's contribution. He was, I think, from St. Andrews, maybe. And so how do you understand that? Well, if the wave is coming in this way and has an electric field in this plane, then every atom along here, every atom along the interface and into the material, all has the is all making every electron and every atom is oscillating this way, back and forth. And we saw yesterday when we calculated the dipole radiation that whenever you have a dipole, there's no radiation in this direction. Well, it turns out for X-rays, the refractive index is so close to unity that the alignment here is that if you come in at about 45 degrees, just slightly off from 45 degrees, all of the atoms, all of the electrons are oscillating this way, and there is no reflection, there is no amplitude, they are not scattering. No atom or no electron is scattering radiation or energy into this direction. It's okay for the refracted wave, but there's 0 for the reflected wave, and that comes out of the mathematics. You just go through these things and you ask yourself, when is this equal to 0? So this equal to this, you call it the Brewster's angle. So just make the numerator 0 and follow it through, and the math is actually just a little bit of algebra. It's quite simple. And this is what you'll find in general, not just for X-rays, for the refractive index. And so I guess for visible light, it's something like 60 degrees or something like that. But if you've ever worked with solid-state lasers, like a ruby laser or a neodymium laser, where they have a rod, neodymium YAG rod, they're always, the rods are always cut at Brewster's angle, so that the light going back and forth in the laser cavity isn't experienced reflection for one polarization mode. For the other electric field, there is a little bit of a reflection, the usual 4%. On each pass, on each end. So as the wave is going back and forth, there's all possible polarizations, but the polarization which has no reflection quickly wins out, and it's going to be the larger amplitude because the other polarizations are slowly losing their amplitude. And in this avalanche effect of lasing, stimulated emission, that polarization wins, and what comes out of the laser is very well polarized. So that's a use of Brewster's effect in visible light, and for us, this is also a way. If you want to do some polarimetry and you have radiation which is not polarized and you'd like to make it polarized, this is a way to do it. Okay? And I gave some example of how we goofed one time building a synchrotron beamline, and we were going to have different splitters and go in different directions, and did we get a surprise? because we put a mirror at 45 degrees and we had horizontal polarization, and there was just no radiation in that branch line. Okay, so that's Brewster's angle. You can see it's a little bit less than 45 degrees. Okay, but it's a pretty small amount. Yes?
The back reflections, the back reflection.
The back reflection this way?
No, that's
This is the incident wave.
and don't you have somehow this direction? Because the electron, the atoms may go selecting, so it's like the potential swing.
Yes, but our boundary condition said that the back reflection was in this direction. It's not, this is an angle, the surface is here, so the reflection, the light's coming in this way, let's say this way. There's no reflection this way, the reflection is this way, because this is a smooth surface. So just think that this is a mirror, and you shine the laser pointer on it, it's going to go down. But it's the amplitude that's changing to 0. Yeah. Okay, what else? Oh, we talked about this yesterday. This was an example of using total external reflection in 2 curved mirrors, one focusing in one direction, one in the other direction, and then you can get a real image. And these have been used in laser-produced plasmas, like fusion plasmas, and they're used in synchrotrons all over the world, and they're used in free electron lasers now. This is the slide I went back to show you before. And then there's just 3 slides at the end. This is sort of, you can see that this is, we've already been through this, basically, but this was our wave equation with the J term, and we had to take the partial of J with respect to T, and we went through. It's a little bit more math. But anyway, we got our refractive index, and then I wanted to look at some special cases where the wave equation, let's say if we're propagating in vacuum, this is our wave equation where the electron density is, the density is 0. This is our wave equation, and this is, again, we make these operators and we say that this has to be finite in order to be 0, but have a finite wave. This is 0. That gives us this relationship. Omega is equal to plus or minus kc. Right? This has 2 pi f, and this is 2 pi over lambda, and you get this. Okay? And then you'll see that this will change in a moment to c over n when we have another example with, in this case, many electrons, but they're all free electrons. So this would be like a plasma. Okay? There'll be ions there too for neutrality, but the ions are so heavy that they don't oscillate so much. Even for visible light or X-rays, it would still be accurate to do this. And now your refractive index, all that summation and all of the frequencies and everything, there's no binding energy. Omega s equals 0. The omegas would cancel, and all you would be left with is this part. This was in front, and there was some factor after it which had to do with the atomic scattering factor is now unity, 1. And so this refractive index, all of this, all you plasma people in the room recognize that there's a plasma frequency here, squared. And so the refractive index at high enough frequency is this quantity. And now you put that into the refractive index. And again, you say, I want finite electric field to know what are the natural modes that propagate. For this to be 0 with finite fields, this has to be 0. And again, you assume that you have some plane wave of this form so that these operators take a form. And this gives you this dispersion relationship. So this is the dispersion relation for a transverse wave propagating in a plasma of many free electrons. Okay? And this would be the dispersion relation. And it says that for frequencies omega, below the plasma frequency, there is no propagation of the wave. It just exponentially damps. And this is this dispersion as a function of k. And so if you get to high enough k, if this is small enough wavelengths, so k is very big, this term won't matter, and you're approaching propagation in vacuum. Okay? But anyway, so this is the propagation. This is the dispersion relation for a plasma wave, transverse wave in a plasma. So a simple case. And what's next? So now you have some material of atomic density n sub a, many bound electrons, what we saw before. So this is all starting to look very familiar to us now. You know, we set this equal to 0, we solve, and now we have the 1 over n, so f lambda equals c over n, so that's our dispersion relationship, except that now n, the refractive index, depends very much on what the frequency is, okay, as in this thing. So I think that's next to the last slide. What's left? Oh, this was just to get a handle on what these numbers were. Just to say that if you're, like the last case, you're in a material, and there is some atomic density, and there are resonances in that, but you're at a very high frequency now, so hard X-rays or something, so that this is much bigger than this, then you can just start to simplify this thing and put in some numbers for atomic density. So around 10 to the 23rd atoms per centimeter cube. This should be on the back cover of your book. If you have that. I think it's still there on the paperback. Anyway, if you put some numbers in and you figure that this sum here is to z or something like that, you could estimate, get your own estimate of what is delta. And you can do beta too. And so just some comparison. And I think that's the end of it, yeah. So we did it, we're done. So we're open for question and discussion. And also some feedback on what we should do with the extra lecture tomorrow. So one suggestion was that we simply have a discussion. People come, bring up, if we do that, you should come with some questions, either on material that we did or something that we didn't talk about is okay too. And it'd be better if I know something about it. Some of the plasma issues we didn't talk about so much. So if you're interested in the plasmas, you might flip through the book and see in chapter 6 what kind of things interest you, or some of the people who are working with lasers, you might bring up coherence issues.
Yeah, I think that's a good idea, because one later in the big bill is going to be talking about high harmonic generation, where you've got plasmas. So it's useful if people know the topic. But also we haven't really talked about X-ray lasers, plasma-based X-ray lasers.
Yes.
I think that might be
okay.
something that
So that would be fine. So were you bringing up the high harmonics because you wanted me to say something, or you didn't want me to
Well,
say
I know
something?
Bill's going to say something.
Yeah.
But,
Okay, so I won't say anything then.
Yeah, but bringing the concepts of plasma properties will come later.
Okay.
But maybe also coherence issues.
Yeah, so coherence issues are really important in many applications, but I don't know if everyone's...
Me too. I go for the current.
Oh, okay. Okay, so I'll try to get a few slides together, but we'll mainly have it as a discussion, but I'll put some slides in there. Actually, a blackboard would probably be
And
better.
just plasma-based X-ray lasers. They will not be covered here.
What is it?
Plasma-based X-ray lasers. These
Yeah.
neon and nickel lights.
Yes, right. So okay, so I'll do that. Yeah. In fact, yeah. So you know some of that is in the book, but there's also probably again we have some things on that memory stick. I don't know where the memory stick is, but anyway, yes. Okay, so that's good feedback, and then we can have discussion. So if you have any thoughts, other thoughts, the sooner you tell me, the better. Okay, thanks. Okay, so I guess it must be lunchtime, is that right?